Hey guys, I'm going to be doing a few videos for you here over break. The goal is to complete 2 sets of notes, so we'll take care of those with these videos, and then you'll have homework at the end of the packet. I think the last 2 pages are homework that you have to do on your own. So let's talk about exponential growth first. Now this will probably be broken up into 2 or maybe 3 videos, but we're going to have to really talk about this first example in depth. The question we need to answer with this lesson is, how can we use exponential functions, which we know about, we've dealt with those for the last couple of days, to represent real-world growth models? So that's what we're going to be doing now. How do these actually work in the real world? So let's start off with this example here. James owns a chain of restaurants, and he operated 200 stores in the year 2000. The rate of increase is 10% annually. How many stores does the restaurant operate in the year 2007? All right, so let's start off just by making a table here. We know that usually when we graph things, we start with a table. So we'll make this side be the years after the year 2000, because we're going to start tracking the growth of his business year by year. And the other side is just going to be how many stores. This is how many stores James is operating in whatever year we're talking about. So let's start off just easily here. Will be the year 2000. Well, that's 0 years after 2000, and we know that in the year 2000, he's got 200 stores. Now the problem is that every year the amount of stores he has increases by 10% of whatever is there at the time. So in the first year after 2000, which is going to be the year 2001, he's not just going to be operating the original 200 stores, because those aren't going anywhere. He's also adding on to that 10% of whatever the stores is that he has, right? So he has 200. He's going to add to that 10% of 200. So let's break this down. We've got his original 200 stores, and then he added 10% of that 200 to it. So this would be the 200 stores plus the 200 times 0.1, which would be 10% of that. Now, instead of calculating that number right now, because we don't really care how many stores it was in 2001, we're going to see how this pattern starts to form over the years. Now, we can rewrite this. If we look at this like we have some of our binomials, we could actually factor this. Right? We've got an addition sign here. So what is something that this component shares that this component also has in common? Both of those pieces have a 200. And if we divide this component by 200, we'll have a 1. And if we divide our other component by 200, we'll still have that 0.10. So this ends up being written as 200 times 1.1. And we're able to condense it that way for the first year after 2001. Let's see what happens in the second year after 2001. So in 2002, we will be 2 years after the year 2000. Now, how is this going to be any different? We have our initial $200 times 1.1, because that's what we're dealing with now. We still have that 200 times 1.1, that's what we have from the year before. Now we're going to add to it that amount times 0.10, because we're going to take 10% of that now. And we can do the same thing we did in that last year to this year. We can factor it. And when we factor this piece, we're going to pull out a 200 times 1.1 from both this term and this term. And what we are left with is a 1 plus 0.1. So that ends up equaling 200 times 1.1 times 1.1. Or another way to write that would be 200 times 1.1 squared. And that's where the connection starts to emerge. When we get to the next year, 2003, well, that's going to be 3 years after the initial amount of restaurants that was opened. And we can just immediately write, we're starting to see this pattern, that's going to end up being 200 times 1.1 to the third power. And it doesn't matter how many years we go with this exponential growth function, whatever the number of years is going to be 200 times 1.1 to the t, or however number of years it is, power. And we see how if we just keep doing that pattern, it's going to keep emerging. We're going to keep being able to factor that string of 200 times 1.1s, right? It's just going to keep happening, so we can keep condensing it and writing it this way. So the question is asking us, in the year 2007, when it's 7 years later, then how many stores will they have opened? Well, that's going to be 200 times 1.1 to the 7th power, which equals 389.74. And we've got a decimal. We know that you can't open up 0.74 stores. You can't open up just half a store or just 74% of a store. So because they didn't open a full extra store, the amount of stores that was opened was 389 stores. And that's how many exist in the year 2007. So I'm going to take the rest of this video just to write down our standard formula. And that's a really good example for you to come back to in the future. But based on this example and others like it, we can start to generate a standard formula for how to calculate these. This exponential growth, it's not an accident that that kind of condensed the way it did. We're going to say that our total amount is always going to be equal to whatever our principal amount is. That's what we started with. So in this case, it was 200 restaurants times 1 plus the rate. In this case, it ended up being 10%, all to the t over n power, where t is the amount of time and n is the amount of occurrences that there are in that unit of time. So in this case, the amount of restaurants was increasing by 10% every year. Now, if that was happening more often than just once a year, we would change n. But in this particular scenario, n is just 1 because we're only doing this once per every unit of time. So using this formula, we're going to start to deal with the examples for the second part of these notes. I'll do that in the next video.